Okay, in this lecture, we're going to talk about thermodynamics. We introduced thermodynamics in General Chemistry 1, but now we're going to talk about entropy and free energy in terms of predicting whether reactions are spontaneous. Right? In General Chemistry 1, we talked about thermochemistry, which was studying heat exchanges that accompany chemical reactions and chemical processes. And in that, we defined a property called enthalpy, right? Where enthalpy is really a measure of energy exchanges when bonds are made and broken in chemical reactions. If you go from stronger bonds to weaker bonds, energy is released as heat. If you go from weaker bonds to stronger bonds, energy is absorbed from the environment. So enthalpy was measured, right? It's measured as exchanges of heat between the reacting system and the surroundings. Okay? And so that's what we looked at in General Chemistry 1 was enthalpy changes. And we said that reactions could be exothermic if they released heat to the surroundings. That is, the surroundings get hotter. Or they can be endothermic. They absorb heat from the surroundings, so the surroundings get colder, right? And so we talked about those kinds of processes, right? And in general, we associated exothermic processes, those that released heat energy, with processes that moved forward. But what we find if we look around is there are some processes where that isn't the case, and some that we're familiar with. Right? One of these is the dissolution of ammonium nitrate. Right? Ammonium nitrate is a solid. If we put it in water, it dissolves very quickly into ammonium ions and nitrate ions. Right? But ammonium nitrate is the stuff in those first aid cold packs, right? It's also a fertilizer, but it's the stuff in those cold packs in first aid kits. And so we know that when this dissolves, when you break the little packet of water that's in there, that the products get cold, right? They feel cold because your ankle that is injured is the surroundings. I keep getting surroundings too close to the edge, right? And so heat is being absorbed from the surroundings into the process to make the surroundings feel colder as the process proceeds. Now, this dissolves very readily. So this is a process that is both endothermic, that is, it is absorbing heat energy from the surroundings, and spontaneous. Right? Here's another example of something that we would consider more a typical chemical reaction. Barium hydroxide comes as an octahydrate. That is, right, in these hydrated solids, the water actually becomes part of the crystal structure, right? And so barium hydroxide makes an octahydrate solid, and it can react with ammonium thiocyanate, right? And the stoichiometry is 2 to 1, and right, that reacts spontaneously. This is also a solid. If you mix those two solids together, they rapidly liquefy, and you get barium thiocyanate plus water, right? And if we balance this appropriately, it is 10 water, right, which quickly liquefies, and 2 ammonia, which is gaseous, right? Now, this is another process. We mix these together, they immediately liquefy. The reaction is clearly spontaneous. But it also gets cold, so it is also endothermic, right? Because it creates a gradient so that heat flows from the surroundings into the reaction, right? So we can see that being exothermic, giving up heat energy, is not always enough to predict whether a process is going to be spontaneous. And so clearly we're missing something if we're just looking at the exchange of heat energy. There must be another thermodynamic factor that helps predict whether reactions are going to be spontaneous. Heat is only part of the equation. So let's look at the other factor. The other factor that we didn't talk about before is a property called entropy. Right? The entropy of a system is a measure of the number of ways that the energy can be distributed in a system. Okay? So the more ways you can distribute the energy, the higher the entropy. Right? And so, let's just look, right? So say we just have a system of 2 particles, right? They could both be moving this way at the same speed. That's one way, right? They could both be moving this way at the same speed. That's another way, right? They could both be moving this way. They could both be moving this way, right? At the same speed. But now we could consider them moving in opposite directions. They each have the same average kinetic energy that way, right? We could consider them moving one in this direction, one in that direction. All of those are ways of distributing the chemical or the potential energy in the system, right? They could be going this way and that way, right? All the different ways we could do this from all the different positions add up to ways that you can distribute the energy in a system. And that contributes to the entropy of that system, okay? And so it ends up that higher entropy is a favored state, right? So we've got really sort of two things here now. Okay, if we consider some factors that affect entropy, right? One of those factors is state, right? The more free molecules are to move, the more ways the energy can be distributed in the system. Okay? And so that means, right, if we have molecules in a solid where there's very little freedom of movement, right? The molecules are not stationary unless we're at absolute zero, right? And so we have a low entropy. If we have our molecules in a liquid state, right, they are freer to move within that liquid, but because the liquid has a defined volume and they're very close together, their movement is still somewhat restricted, right? We have a medium entropy, right? But if the molecules are in a gaseous state, those same molecules, so that they're free to move anywhere in the container and bounce off the walls and bounce off of each other, that state has a high entropy. Another thing that can affect entropy is concentration or pressure, right? Remember, pressure is a measure of the concentration of gases, right? More molecules occupying the same space reduces the ways energy can be distributed on a per mole basis. Okay? So if we have, right, two containers, right, one of which contains more molecules, either in solution or in the gas phase, and one that has fewer molecules, there are more ways per mole of molecules to distribute that than this. And so, right, a lower concentration or a lower pressure is a higher entropy state. Okay? And so let's go back and look at our reaction of our barium hydroxide octahydrate with our ammonium thiocyanate to make barium thiocyanate, which can dissolve in the liquid water we're producing, and we get ammonia gas, right? So note, right, we said that this absorbs heat energy, so it was endothermic. Right? If we put our hand on the flask at the end, the flask would feel cold to us because this reaction is pulling heat energy out of our hand to store in these molecules, right? So the internal energy of these molecules is greater than the internal energy of these substances, right? So internal energy has been pulled into these substances, right? That's what made it endothermic, right? So we're going from a low energy state to a high energy state, right? That seems backwards, right? But if we look, we're going from solids to liquids, gases, and ionic compounds in solution, which means these ions are free to move independently in solution, right? So we have, while we may be endothermic, we have an increase in entropy because we're going from solid to liquids and gases primarily, right? Where those particles have more mobility. Okay? Now, the question is, how do we decide, right? Because in general, we think of endothermic processes as being unfavorable, right? Processes tend to move towards states of lower energy, and here we have a process moving toward a state of higher internal energy. But at the same time, an increase in entropy, right, an increase in the number of ways that we can distribute the energy in this system is favorable, right? And so at the moment we have, right, a system where our enthalpy is unfavorable, our enthalpy change is unfavorable, but our entropy change is favorable. We could have the opposite. Processes where our enthalpy change is favorable and our entropy change is unfavorable. The question is, when those two disagree, how do we decide which one wins and whether our process is spontaneous or not? The key to the balance was developed by a chemist named Josiah Willard Gibbs, right? And I do that just because it's one of the great names in chemistry, right? So Gibbs figured out the overall balance and came up with the concept that we now call the Gibbs free energy, G, right? The Gibbs free energy is equal to the enthalpy minus the absolute temperature times the entropy, right? Now, these are not things that we can usually measure in abstract. The only thing that can be measured in abstract is entropy. So we tend not to do this in terms of absolute numbers, but we tend to do it in terms of change numbers, right? So the change in Gibbs free energy is going to be equal to the change in the enthalpy minus the absolute temperature, for working at constant temperature, times the change in entropy. And, right, so if delta G is less than 0, that is negative, the process gives up overall free energy, and that is a spontaneous process. If delta G is greater than 0, that is, it is positive, then our reaction is non-spontaneous in the direction it's written, which would mean it would be spontaneous in the reverse direction. Okay? So the Gibbs free energy is the property that lets us balance between delta H and delta S under conditions when they disagree. If they're both favorable, the whole process is going to be favorable. No problem. If they're both unfavorable, the whole process is going to be unfavorable under any conditions. But if one's favorable and one's unfavorable, it ends up that the temperature becomes critical, because the temperature affects that delta S term and makes that delta S term more important.